Inverse variation is really an extension or another angle we could take for applications of reciprocal functions. Because what we really have here is an inverse or a reciprocal relationship going on. An inverse means opposite, okay? So as one of our variables gets big, the opposite happens to the other, okay? So as x gets large, y gets small. As y gets large, x gets small. Now, I hope that sounds kind of familiar because that's exactly the same as a reciprocal function. So this is in essence not a new idea. It's the same idea approached from a different angle. Okay, so the first thing is we write these inverse variation equations in the form x times y equals k, but normally we don't use x and y. Okay, we use practical variables like c and n and t, maybe p for cost, number of people, P for people or N for people, and T for time, where K is the constant of proportionality. Now, constant means it doesn't change, and proportionality means that two things are in ratio or proportion to one another. That's just a fancy way of saying whenever I multiply my two numbers together, I get the same thing. I get a constant value, which means if one of those numbers gets big, the other one's got to be small to get back to the same place. Okay, if you think about the example I used in our last video, I've got a fridge that's going to cost me $1,000. If I can get three friends who I live with to chip in to pay for that fridge equally, well, it costs us $250 each. Okay, so there's four people times 250 has to give me 1,000. If I can get more people to chip in, it costs us all less. But if less people are willing to chip in, it costs us all more. But the constant thing there is that the fridge costs $1,000. Okay, the guy at the electronic shop is not going to say, oh, well, there's more of you or there's less of you, so I'll give you a better price. He's still going to ask for $1,000 for the fridge, whether it's me alone buying it or me and my 5 friends. So the constant is the thing that we keep coming back to that will not change. So these present themselves in a couple of different ways, but often what we have to do is multiply the two variables to find the value of k, if necessary, and then rewrite an equation using those letters that I just talked about. For example, written here, it's C is the cost per person and N is the number of people. Okay, so we'd want to use C and N there, not X and Y. Let's have a look here. So our first example, we're actually given the constant value. Okay, so this 210 here is K. That's our constant of proportionality, because if we read the question, a preschool centre pays $210 to hire a bus for an excursion. If they put 3 kids and a teacher on that bus, $210. I'm assuming they've got a limit to how many people they can fit on there. They couldn't fit 1,000 kids. But if they put 50 people or 60 people and 10 teachers, they're still going to pay $210. So 210 is actually that constant value, which means our cost per person multiplied by the number of people is going to give us 210, which is that form there, xy equals k. We've got our constant already given to us though. Okay, so our first thing is find the cost per person when 70 people go on the bus. Well, our cost per person is 210 over n, or to write the other way, the number of people who can get on the bus is 210 over the cost per person. We're dealing with the first scenario here, so our cost is going to be 210 over 70, which is $3 per person. Find the equation connecting C and N. We've actually done that. We've done that beforehand. I always like to box that one to show that it's show that it's very clearly there. We've got not X and Y, we've got C and N involved there, and we've got our constant of proportionality on top there. How much would each person pay? We've got an extra word in here. How much would each person pay when 50 people go on the bus or 75 people on the bus? Again, we would get to a limit here. I'm not sure how large this bus is for $210, but maybe the capacity is 100 people, maybe the capacity is 90 people, but we couldn't say an endless number of people could just get on the bus to make it cheaper and cheaper per person. There would have to be a limit, but we're not told what that is. That is more just a thought exercise. And if you ask something about why 1,000 people couldn't fit on the bus, that would be built into your answer somewhere because there'd have to be an upper limit. How much would each person pay? Well, if n equals 50, our cost is going to be 210 over 50, which is $4.20. And if we put 75 people on the bus, our cost would end up being 210 over 75, which would be $2.80 per person. Now, thinking about this practically, the scenario where I'm expecting to be the cheapest per person is where I put the most people on the bus. And the most expensive is where I put the least people on the bus, which is why 50 people costs more per person than 75 people does. Now, again, we come back to it. How much are we paying for the bus? $210. But how much is each person paying for the bus? Well, that depends on how many people are getting on the bus. We've got a speed, distance, and time example here. So we know that our distance is always d equals speed times time. Now, that's actually, if we rewrite it this way, okay, if I remove d from here, speed times time equals distance, that's actually an inverse variation equation, depending how I write it, where d is the constant of proportionality. Now, if you think about it for a second, if I'm driving from Sydney to Port Macquarie, how fast I go or how long it takes me, those things can change. But how far it is, assuming you're taking the same road each time, how far it is from Sydney to Port Macquarie is always a constant value. There is a distance, a fixed distance from Sydney to Port Macquarie. I could ride my push bike there and take 3 weeks, or I could go twice the speed limit and get there in 2 hours, but the distance is still the same. Okay, so to find our distance here, so we can write this equation. Our speed is 90, and our time is 4.5. I'm going to put it in as 4.5 instead of 4.5, easy to work with. So that means our distance, or our constant of proportionality, is 405 kilometers. Okay, which means that if we want to find the time taken, t is our subject, well, that's 405 over the speed. That's our equation relating those two. Now that we could do all sorts of things with that, right? We could say if I was traveling at 100 kilometers an hour, how long would it take me? It would take me a little bit over 4 hours. If I halved my speed, how long would it take me? Well, it would take me just a little bit over 8 hours. If I wanted to get the trip done in 6 hours, what speed would I have to go? And so on, and we could keep doing those things. But this is the equation here. Once again, we write that equation with our appropriate pronumerals written, t for time and s for speed, not just x and y, and we find our value of our constant, and that always goes in the top of our fraction. I could write it this way, speed equals 405 over time, but what we're really saying here is the time is the dependent variable, so we should write that here. Okay, that's our dependent variable, whereas our speed is independent of time. Okay, we adjust our speed so that we can adjust our time, not the other way around. I hope this has been helpful.